All right, so we're in 14.3 now, talking about the topic of partial derivatives. Partial derivatives are a major portion of this course. So if you think about what you do in single variable calculus, you learn how to primarily take derivatives and integrals. I mean, there's a lot more to it than that, but a lot of calculus 1 and 2, for that matter, can be boiled down to dealing with derivatives and integrals. In the case of multivariable functions, we also have derivatives and integrals, but they look a little different. Partial derivatives are the analog to the derivative of the single variable function. And to investigate that, we're going to look at an example. So let's suppose we have this table here, and what this table represents is heights of waves at open sea. H is going to represent the height of some wave at open sea. That height is a function of two variables. It's a function of wind speed, which we're going to call v for velocity, and it's also a function of time, specifically the length of time that the wind has been blowing at a particular speed. So we're going to call that time t. That's going to be measured in hours. Wind speed is going to be measured in knots. We can write, therefore, h is equal to f of v of t. So h is a function of those two variables. We can tabulate this by making wind speed take up these values here. The duration of a given wind speed is going to be these values here. And then the values in white in the table are going to represent different heights of particular waves. So we're talking about partial derivatives here, which are a type of derivative. And remember, derivatives are rates of change. And so that's the same concept that we want to be able to use with partial derivatives. They should represent rates of change. But think about a single variable function. If you have a single variable function, y equals f of x, then the derivative of y with respect to x is literally the rate of change in y with respect to that one variable x. And that's how you get rates. Units for rates are often, feet per second or pounds per meter or something like that. In our case, we're trying to differentiate a function that gives us height of a wave, and we can only make sense of a rate of change if we differentiate with respect to one variable at a time. So what that means is if I were to want to find the rate of change in the height of a wave with respect to wind speed, that's one possible way of looking at a rate of change. If instead I wanted to look at the rate of change in the height of a wave with respect to duration, the way that we've defined it here, that's another rate of change that I can extract from this. But how do you go about finding a rate of change with respect to only one variable at a time? Well, the trick is to hold any other variables in the function constant or fixed. So here's what I mean by that. Let's take a look at the first case we want to investigate. Let's suppose that we want to know the instantaneous rate of change in wave height, so the instantaneous rate of change in h with respect to wind speed, specifically when that wind speed is 40 knots. Okay? H is a function of both v and t, so we can't let t be floating around and varying. That rate of change for v equals 40 can be a lot of different things if depending on what t is equal to. And so what we need to do is hold t constant. Let's specifically suppose that we're going to let t equal 15. We're going to hold t constant, okay? So we're looking for the rate of change in wind speed if we hold t constant equal to 15. Okay? If t is held constant, if t is equal to 15, then we're restricting our attention to only this column of this table. Nothing else is going to be relevant for this specific problem. And if you notice, these values are only dependent, if we fixed t equal to 15, they are now only dependent on v. Different values of v give me different values in this column. Okay? So what we're going to do is define a single variable function where v is the single variable. G of v is what we're going to call it, and it's going to be equal to f of v 15. So for example, what is g of 10? Well, g of 10 is the same thing as f of 10 15, which is 2. I can read that in the table. Notice because by restricting our attention to just this one column, and thus only restricting our function to only depend on one variable, we've now found a way to think of this two variable function as a single variable function for this purpose. So how do I find that rate of change, that instantaneous rate of change, when wind speed is 40 and we hold t constant at 15? Well, it would still be a derivative, and because g is a single variable function, I can differentiate it using the definition of the derivative from Calculus 1. What is g prime of 40? 40 because that's the wind speed we're looking at. By definition, it's this. The limit as h goes to 0 of g of 40 plus h minus g of 40 all over h. That's the single variable calculus definition of a derivative. But we have an interpretation for this function g in terms of this two variable function f, where one of our variables is held constant. So these 40 plus h and 40 are the values that we're putting in for v here, giving me this. And this should say f right here. That's a typo. F of 40 plus h 15 minus f of 40 15 all over h. Notice that even though we're using a two variable function, there's only one unknown here. It's h, so we can still evaluate this limit. Now the problem in this example is that we're working with a table. We're not working with a function that we have an algebraic expression for, so I don't actually have the ability to evaluate this limit exactly. But in Calc 1 we talk about ways of approximating limits using tables, and that's what we're going to do here. So if you look at the increments that I have in my wind speed near 40, I can kind of move in increments of 10. So I'm going to let h equal positive 10 and negative 10 and approximate g prime of 40 using both of those. In this first set of work up here, I'm using h equals positive 10, and I'm literally just plugging 10 in for the h here and here. To approximate, that gives me 1.1 after doing the arithmetic there. If I approximate h by a negative 10, this becomes 40 minus 10, and this becomes a negative 10 down here. Do the arithmetic. And by the way, if you're still struggling with, sorry, I just realized that typo is showing up all over the place. These should all be f's. That's an f. That's an f. 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 There you go. Where am I getting these numbers from? Well, f of 50, 15, you get that from the table. 50, 15 is 36. That's where that 36 is coming from, and you can see where the other numbers would come from as well. So one approximation gives me 1.1, another approximation gives me 0.9, and because I'm using two values of h that are kind of on either side of 0, I can approximate. I can get a better approximation by averaging these results. So if I average those, I get 1. That means that g prime of 40 is approximately 1 foot per knot. Okay? And again, the units here are based on what the variable of my function is. G gives me the height of a wave in terms of the wind speed, which is measured in knots. Now, if I wanted to do something similar, but this time I want to find the rate of change in the height of a wave, but this time not with respect to wind speed, but instead with respect to duration, then I would have to hold my velocity or my wind speed constant and let t vary. So we could follow a similar process. Define a function p of t, it's dependent on t now, where we hold our wind speed constant, let's say v equals 40. So in this case, p of t would equal f of 40t. And then we can go through the same process. I want to approximate the instantaneous rate of change in my height function with respect to time now, specifically when time is equal to 15. What that means for my table up here is now we're holding wind speed constant, and so we're looking only in this row. And again, if I restrict my attention to just this row, these numbers only depend on duration. So that's where you get a function of t from. Okay, we can go through a similar derivation. For the sake of time, I'm not going to go through all the nitty-gritty because it's the same kind of idea as before. The major difference, though, is that t is the variable that's allowed to vary instead of instead of v in this case. Here I get p prime of 15 is equal to 0.7 feet per hour. It's a rate of change, and it says that if the wind speed has been blowing at 40 knots for 15 minutes, 15 hours, that's what we're measuring time in, is hours, then the rate of change in the height of my waves with respect to time should be approximately 0.7 feet per hour. So the waves will be growing at a rate of approximately 0.7 feet every hour. Okay, two different values, two different rates of change, and if you notice, in both cases, you see how this row and this column intersect. In both cases, I'm evaluating my rate of change here at this intersection point, this 25 right here. Even though I'm not using 25 explicitly, it's at the point 40, 15. And the rates of change are different because I'm looking at a rate of change with respect to different variables each time. Okay? So that idea, we generalize that to get what's called a partial derivative. If f of xy is just any two variable function, if we want to find what we call a partial derivative of f with respect to x at some point a, b, then what we're doing is we're holding y constant. We're setting y equal to the constant b, allowing us to create a single variable function, g of x equals f of xb, where x is a variable but b is understood to be a constant. And then we differentiate this function with respect to x, treating y like a constant, and so we get this definition. This is our limit definition here. Similarly, we can define the partial derivative of f with respect to y at a, b by holding x constant, setting x equal to a. Notice how we're getting a's here and here, and using our limit definition, but having y be the variable that can vary. So that's the definition. Notice the notation here. We're going to talk about different types of notation for partial derivatives, but we use subscripts typically. You notice we're not using the prime notation that you use in Calculus 1, and the reason for that is because partial derivatives depend on what variable you're differentiating with respect to. So you need to have some way of showing which variable we're differentiating with respect to in your notation. Here the subscript of x means I'm differentiating with respect to x. Here if it's y, I'm differentiating with respect to y. Okay. Now these are the definitions of partial derivatives at specific points, a, b. And you do this in Calculus 1 also. You talk about the definition of a derivative at a specific number, x equals a. And then you generalize that and turn the derivative into a function in its own right. And we can do the same thing here. So in my definition for the partial derivative of f with respect to x at the point a, b, you see the a's appearing here and here. If I swap the a out for an x, I get this, okay? And this thing is going to be a function of x and y in its own right. That's why we write it like this. Partial derivative of f with respect to x of xy is equal to this. This is the limit definition. Similar for with respect to y down here. Now in Calculus 1, you spend a little bit of time working directly with this limit definition. You're asked to evaluate some derivatives using that limit definition. And we're really not going to bother much with that here because it turns out that evaluating a partial derivative is essentially as easy and done in the same way as evaluating a single variable function's derivative, which we'll see in the next example. Before I do that, though, I want to talk over some notations that we use for partial derivatives. Just like with the derivative of a single variable function, there's multiple different types of notation you might encounter. So as we've already seen, fx of xy is one way of writing the partial derivative of f with respect to x. But this notation is equivalent to all of these. Notice if I just write fx and I don't write the xy, the point that I'm plugging into the function, it still represents the same thing. This notation here is a very, very common one. We'll use this a lot. It's Leibniz notation. Notice it looks similar to df dx, but we're not using the symbol d. This notation is similar to this one as well. This is called a differential operator. It's kind of like if you write d dx and then a function next to that, it means take the derivative of that function with respect to x. It's the same idea here. This is saying take the derivative, the partial derivative of this function f of xy with respect to x. Sometimes instead of an f, we'll have a z, specifically if we've specified that z is equal to that function f of xy. So you might see the partial of z with respect to x. That's typically how we read that, partial of z with respect to x. These three notations are a lot less common in this course. They show up in other applications. The 1 here is just indicating that we're talking about the first variable in order as you read them. So the 1 would correspond to x. D1 of f, dx of f, these are also a lot less common, but they do show up in specific disciplines a lot more. And then here's all the equivalent notation for, differentiating with respect to y. Okay, so it's been a lot of talking and a lot of, deriving. We haven't done any examples yet. So we're going to look at an example because I want you to see what actually taking a partial derivative looks like. You're going to be doing a lot of that in this course. The trick is just to remember what we're doing with partial derivatives. If I want to take a partial derivative with respect to x, then I hold y constant. I treat it like it's a constant, and then I just do the derivative as I would in Calculus 1, but with respect to the variable x. So here, we're asked to do a couple of things. I'm given this function, f of xy equals x squared y plus e to the xy power. And first thing I want to do is differentiate this function with respect to x. Looking at what I have here, I'm going to treat this y and this y as if they were constants. Think of them like the number 2 or something like that. And then just differentiate with respect to x. So fx of xy will equal, treating y like a constant, I have an x squared. The derivative of x squared is 2x. And then the y being a constant is just there. Okay, plus e to the xy. If I differentiate this with respect to x, treating the y like a constant, the y is what would come out, e to the xy. Again, as you're getting used to this, if you're struggling to see where I got this from, it's sometimes helpful to actually write a literal constant in for y. Write a 2 in there, okay? And then you should see that, e to the 2x is going to have a derivative of 2e to the 2x. Just make sure in your actual answer it's a y, not a 2. For this one, fy of 1, 1, I first would evaluate fy of xy and then plug a 1, 1 into the result. Okay, so we want to differentiate with respect to y this time. Again, y is the variable now, and x is what's being held constant. So x squared would be a constant in its own right as well. What's the derivative of x squared y with respect to y? Just x squared. And then plus e to the xy, again, x is being treated like a constant, so we get plus x e to the xy. Now, I just plug a 1, 1 into that. So that would be 1 squared, or 1, plus 1 times e to the 1 times 1, or just 1 plus e as a result. So here's one answer, here's the other. Okay? Notice it's very, very straightforward. It's easy to do if you're comfortable with derivatives, just regular derivatives from Calc 1. Holding one variable constant might take a little bit of getting used to, but I think most people tend to get used to that pretty quickly. So we'll do some more examples of partial derivatives a little bit later, but what I want to do is move on to a geometric interpretation of what the partial derivative is, because right now we've been addressing it as a rate of change, and that really is the most important way to understand what any kind of a derivative is, partial derivative or otherwise. However, in Calculus 1, we do spend a lot of time talking about the geometric definition of a derivative. We talk about it as a slope of a tangent line. Now, we can actually come up with a very similar definition here, but we just need to be very careful about what we mean when we say tangent line. So let's suppose that we have some function, z equals f of xy. Functions of two variables frequently have graphs that look like surfaces. So let's suppose S is the surface that would be given by this function. It's the blue surface that's showing up here, okay? let's suppose also that if I plug a specific point a, b into my function, that the result, the output, is c. So that forms a point in 3 space, a, b, c, and that point by where it came from would have to be on my surface. So there's the point a, b, c right there. Okay? Now, what do we do when we're taking a partial derivative? We're holding one of our variables constant. So, for example, if I wanted to hold y constant, if I set y equal to this constant b, in 3 space, if I look at the graph of that equation, y equals b, that's the graph of a vertical plane. It's the plane that would contain these two dotted or dashed lines right here. It'd be a vertical plane passing through the surface, kind of cutting through it. And that plane would intersect this surface S in a curve, which here is labeled C1. Okay? Now, the way that we defined the derivative, in fact, I'll go back there. Over here is by holding one variable constant, we were reducing this down to a single variable derivative. And so the same interpretation holds. The derivative, the partial derivative of f with respect to x, which is when we would hold y constant, specifically when y is equal to b, would represent the slope of this tangent line right here, which is being called T1. It's a line that's tangent to that point ABC, on the curve C1, which is the trace. Oh, sorry, I'm kind of mincing my words. It's the tangent line to the trace of C1 in that surface. So you can kind of see how it kind of hits that curve C1 at the point P and is tangent to it. Similarly, if we hold x constant, like we want to take a partial derivative with respect to y, if we hold x constant, specifically set x equal to a, then x equals a is another vertical plane that cuts this direction. It's going to slice through our surface, creating another curve, which we call C2. The partial derivative of our function f at the point AB is going to give us the slope of this tangent line here, T2, this tangent line to the trace of C2 in our surface at that point ABC. Okay? So there is a geometric understanding of what tangent lines are to surfaces, but notice those tangent lines can have different slopes depending on which direction they're going as they hit that point. So this one's going in this direction, this one's going in a different direction. That's kind of how we interpret that in a geometric sense. Okay? I think what I'm going to do is stop this video here and then pick up where I left off in the next one.